In my talk, I would like to introduce two programming tools for algorithmic music composition, simulation, and notation. Before we dive in, I want to clarify that my talk doesn't specifically focus on electronic music. Instead, it aims to demonstrate how programming languages in general can help us understand and create musical structures and concepts in a more abstract manner. This approach opens up vast possibilities for composers beyond the relatively simplistic methods of layering up digitized sounds to create compositions. Pioneers of electronic music like Clarence Barlow, Yanis Xenakis, Karlheinz Stockhausen, and many others often employed algorithmic composition techniques not only for the macro structure of their works, but also for generating their sonic material. The tools we'll discuss today greatly simplify the technical aspects of their underlying software, allowing users to concentrate on the musical and creative aspects of their work. Both tools have been written by myself and they are still under further development. My talk is divided into two main sections. In the first section, I will introduce the tools, and in the second, I will demonstrate a real-world example of algorithmic composition using a computer script that we will write together. Specifically, we will simulate a well-known piano composition by Olivier Messiaen, namely the second movement of his 4 studies in rhythm titled Modes de valeurs et d'intensité. This demonstration will be done in the Python programming language. For those unfamiliar with Python, I will very briefly explain most of the code as I go along. However, due to time constraints of the festival, this surely can't be a comprehensive programming course. I hope, though, that this talk will spark your interest in further exploring the techniques I present here. So what are these tools and how can they assist us in our music creation? To answer these questions, let's first consider the question, what is algorithmic composition? In general terms, we can define algorithmic music as music where decisions regarding its development strictly follow a set of predefined patterns and rules. These rules can influence anything from traditional musical elements like pitch, duration, and dynamics to more abstract aspects such as the gestural or spatial characteristics of sound. Although algorithmic music, in a broader sense, is an established discipline in music making, computer-aided algorithmic composition is a field of artistic work and scientific research that dates back to the mid-50s. Pioneers like the composer Leon Hiller paved the way for using computers as a tool for composition. His fourth string quartet from 1957, generally known as the Iliac Suite, as it was composed on the Iliac I computer at the University of Illinois, was the first computer-aided algorithmic composition. Fast forward a few decades, and the 80s and 90s saw rapid development in computer software for score-based and audio-based music production. Two such software innovations from the foundation of the tools I'm introducing today are the MIDI protocol, which standardizes communication between a wide range of digital instruments and computers, and the LilyPond compiler, which is used for engraving high-quality music scores. Both these software marked significant turning points in the creation of music using personal computers. Many of you might already be familiar with MIDI, but for those who aren't, here is a brief overview. MIDI, which stands for Musical Instrument Digital Interface, is a communication protocol developed in the early 80s and is still widely used across various areas of music today. Most commonly, you'll encounter MIDI in digital audio workstations. However, MIDI is much more than just a DAW component. It's a protocol that allows data to be generated, sent, and received by various digital devices. It also can be programmatically created by other computer programs. One particularly exciting way to work with MIDI is, in my opinion, by using a programming language to generate the MIDI data, which opens up a vast range of expressive possibilities. Handling raw MIDI data, however, can be cumbersome and tedious, and this is where a software that simplifies working with such data becomes invaluable. In a sense, such programs should manage low-level MIDI data so that we can express our musical ideas more easily. In this lecture, we will learn about one such abstraction layer for the Python programming language, called Milton, named after the composer Milton Babbitt. While there are numerous other packages for working with MIDI available for Python, the Milton package stands out for its very minimalist design. To give you a better understanding of how Python and MIDI work together, I will walk you through some simple examples using the MIDI package to generate real-time MIDI data. For those interested in diving deeper into Python, there are plenty of resources available online. In fact, there is also a very active Python community in Tehran that regularly organizes meetings and conferences on Python-related topics, both in person and online, which could be a good place to learn more about programming in Python. Now, let's dive into our first example. For these examples, I use the Python Interactive Interpreter, which simplifies running and testing and correcting smaller pieces of code. Later in the second part of my talk, when we simulate Messiaen's piece, we will create and use a Python source file. The first thing we need to do in any Python code when using specific packages is to tell Python that we are going to use them. We integrate the functionalities defined into a package by importing the package into our running code, which is done using Python's import directive. Here, I have already installed the necessary packages on my machine, so the only thing I need to do is just importing them by writing import Milton. After this line, we have now access to all the functionalities of the Milton package. To use any of these functionalities, we write the name of the package followed by Python's dot operator and then the name of the object from the package. Let's use this pattern to get the current version number of the Milton package. The dot operator in Python is used to access functions, variables, and classes defined within a package's modules, which in Python terminology are individual source files that constitute a whole package. For instance, to access the note function, which is defined in Milton and is responsible for generating MIDI note and chord data, we would follow the above pattern for accessing package objects using the dot operator. The result is a function object from the Milton package, which is not executed yet. Now, before we can hear our first note, there is one more step we need to take care of: initializing the real-time module of Milton. This allows us to hear the results of our work directly when we run the Python code without having to write them to a MIDI file first. To do this, we call the init function of Milton's real-time module. Note that executing a function in Python requires putting parentheses after the function name, which causes the function to be called. That's it. We are now all set to create and play our first note. To do this, we'll use the note function I just introduced. But first, a few further words about functions in Python. Functions are objects that encapsulate blocks of code designed to perform specific computations and return a value or output. Much like mathematical functions, Python functions can also take inputs referred to as arguments in programming terminology, allowing us to interact with functions and control their output. The syntax for calling a function in Python is similar to the mathematical notation of functions. For example, if we want to define a function that takes a number as input and returns its square, we express it mathematically as f of x is equal to x squared, where f is the name of the function and x is its argument. In Python, we define functions using the def keyword followed by the name of the function, a pair of parentheses in which we specify any inputs to the function, and then define what the function does and what it returns inside of its body. So we can define the square function like the following. Define square, which is the name of the function, takes one argument num and return num's square. And we can call our function by passing it arguments. Now back to our node. The node function we are going to call is already defined within the Messiaen package, so we don't need to define it ourselves. The node function takes 5 optional inputs in the following order. The pitch of a note, which should be a MIDI key number or the name and the octave of a note. The onset time in seconds to be passed for a note or chord to be played starting from 0. The duration of the note also measured in seconds. The MIDI channel, which is not important for our work today, and the velocity of a note, which represents how hard and fast a key on a MIDI keyboard is pressed. We could describe this as the loudness of the sound, measured as a 7-bit value resulting in 128 different loudness levels, with 0 being the softest and 127 the loudest. All these arguments have default values as we can see, which means if we do not specify a value for them, the default values are used. These default values are 60 for the pitch, the onset 0, a duration of 1 second, MIDI channel 1, and velocity being 127. Knowing this, let us create a single note, the middle C on the piano, with a MIDI key number 60. To do this, we need to call the note function. I assign the return value of our function call to a variable named C4. This allows us to define this note once and reuse it wherever we need it. If we now print the value stored in the variable C4, we will see something similar to the following. These key value pairs are the return value of the note function call. These values are later used by the main processing function to generate the actual sound. Now, let's play the note using the main function of Messiaen, the pros function. The most important argument to pros is the note or notes we have created. This function processes everything necessary under the hood so that we can immediately hear our note. You might be wondering about the square brackets around our C4 variable in pros. To make the pros function capable of handling also a sequence of notes or chords, it has been designed to expect a list of notes. In Python, square brackets are used to create an ordered collection of data called a list. For example, we can create a list of numbers like this. A list can contain any Python object, including variables like the C4 name we defined. The pros function expects such a list as input, which must contain either notes or other lists of notes, thus enabling us to create polyphonic structures. Now, what would happen if we put two notes, say in an interval of a perfect fifth, inside the pros function's first argument? The first note is C4, and the second note 7 semitones above the G4 note. We hear that putting more than one note in the list will cause all of them to be played simultaneously, as a chord. We can use this to create a C major chord. But what if we wanted the four notes of the C major chord to be played as an arpeggio in sequence rather than simultaneously? Remember the arguments to the note function. We had an argument called onset, which specifies the time point at which the note should be triggered. 0 means immediately, 1 means 1 second after the beginning, 1.5 means 1.5 seconds after the beginning, and so on. Let's modify the code by specifying the onset arguments in the note functions so that the notes play sequentially as an arpeggio, with each note following the previous one with a time difference of 1 second. We can play this sequence faster by having each note come in after a quarter of a second. There is an overlap of notes since the default duration of a note is 1 second if not otherwise specified. To avoid this overlap, we can adjust the notes by passing the duration argument to each note, giving each note a shorter duration of a quarter second. This leads us to an important aspect of Milton. Let's think for a moment about what just happened. Including more than one event in the list argument of the pros function results in them being played simultaneously. Even when we specify different onsets, all really is happening is that the notes are triggered at the same moment, only the sounding of some notes is delayed by some offset time. In Milton, we also have the possibility to place an entire sequence of notes packed inside a list in place of a single note within the list argument to pros. For example, I can pack the notes of the C major arpeggio and an F major arpeggio, 1 octave lower, into two separate lists and then pass both lists to the pros function. This results in both arpeggios being executed at the same time. And so, by passing a list of lists of notes instead of a list of individual notes to the pros function, we can easily create a polyphonic structure. As we already saw in our first note example for the pitch argument of the Milton note function, in addition to MIDI key numbers, we can also specify note names as strings. In Python, strings are sequences of characters enclosed in double or single quotes. For example, to specify the middle C on the piano, we used the string C4, which represents the note name and the desired octave. Similarly, to specify the 440 Hz A, we could use any of the following forms. To demonstrate a bit more elaborate example, I would now like to generate the first three measures of Bach's two-voice invention number 8 in F major. The first thing I do is to define the pitches and their durations for the right hand and for the left hand. Building the notes for both voices of the right and left hands is easily done by using a loop. In the following code for generating the notes, I use two additional constructs provided by the Python language, which I would clarify very quick. A for loop is a central and important coding construct that exists in almost every programming language, though some, like the programming languages Haskell or Scheme, do not have it explicitly. With a for loop, you can iterate over each element of a list and specify an action to be performed on that element, such as passing it as an argument to a function and gathering the result in another list. For example, if I wanted to iterate over a list of numbers, calculate the square of each using our square function defined earlier, and gather the results, I can first define an empty list, and then iterate over the numbers and save the result of calling the square function into the empty list. Adding a new value to a list is done by using the list's append functionality. Since gathering results from a for loop iteration into a list is a very common task in programming, Python provides a shorter way to achieve this in one line. This syntactic shortcut, which exists in some other programming languages as well, is called a list comprehension, and it is what I will use in the Bach example to build the lists of nodes for both the right and the left hands. For instance, to create a list of square numbers using a list comprehension, instead of explicitly looping and gathering squares through a list of numbers, we can do this in one line. This way, the step of explicitly appending each squared number to a list and modifying the list on each iteration can be omitted, resulting in cleaner, faster, and more concise code. The next construction is the zip function, which pairs items from multiple lists together. For example, if you have a list of numbers and a list of strings, zip will combine them into pairs like this. I use the zip function in the Bach example to create pairs of pitches, ansatz, and durations and iterate over these pairs for generating the final notes. The ansatz are computed from the defined durations using a Python function called accumulate, which returns accumulated sums from a list of numbers. This function also has an argument for the initial value to start the accumulation, which defaults to 0. With this knowledge, I can define the notes for both hands now using two list comprehensions, gathering pitches, ansatz, and durations. By passing both lists to pros, we have the first 3 bars of the invention completed. The next Python package I would like to introduce briefly before diving into the main part of my talk is the Clarence package. The Clarence package, which is named after one of the pioneers of computer-aided algorithmic composition in Europe, Clarence Barlow, simplifies and Pythonizes the creation of LilyPond score files. LilyPond is an open source and highly versatile music engraving software, or more precisely a markup language. Unlike more well-known notation software like Finale or Sibelius, where you typically use mouse clicks to assemble your score, in LilyPond we create a source file, which is then compiled by LilyPond to generate the resulting score. For example, to generate a simple sequence of notes in LilyPond, we might write something like this, which, when compiled, produces the following score. Or as another a bit lengthier example, to write the couple of bars from Bach's invention, I write the following LilyPond code. Using LilyPond brings many benefits. The overall appearance of the scores and the spacing algorithms used in the open source LilyPond are very sophisticated compared to many commercial notation software. In fact, the developers of LilyPond have aimed to produce scores that are as elegant as the beautiful hand-engraved scores of the past. For those interested, I'll share a link to an insightful article from the LilyPond development team where they discuss their work on LilyPond. Also, unlike other software, a LilyPond score file is not a binary file but a simple text file. This makes it much smaller in size and makes it easier to save our work incrementally, perhaps using a version control system. It also allows for easy collaboration with others, perhaps working on the same score at the same time. However, there is a small downside to using LilyPond. Learning the syntax and working efficiently with it often involves a fairly steep learning curve, and you will probably need to consult the LilyPond manuals over and over while working on your score. Also, as you can see from the Bach example, writing even a short LilyPond file can become somewhat confusing very fast. And most importantly, for the algorithmic composer, since LilyPond is a markup language and not a programming language, producing scores algorithmically with it is not straightforward. This is where our next package Clarence comes into play. Clarence simplifies the creation of LilyPond files, handles many of the burdens you would otherwise have to manage manually, and allows you to use a simple Python script to generate even larger scores programmatically. The Clarence package is designed with one very important goal in mind: to abstract away as much as possible from LilyPond for you, or to put it in other words, to allow you creating LilyPond scores using only your general Python knowledge. It is thus very minimalistic in terms of its programming interface. In fact, the whole package includes only two main components: a main processing function called pros, and the class which represents one musical staff, for instance for a single instrument, called part. The pros function is responsible for processing everything and providing the finished score, similar to how the pros function worked in Milton. As said, the part class represents one instrument or voice. In Python, a class is a blueprint from which you can create many instances. We can create instances of a class by calling the class very much like we did with functions, with the necessary arguments if the class accepts any. For example, here is a hypothetical class called composer, which we call twice to generate two instances of a composer and assigning them to two variables. This hypothetical class accepts two arguments, the name and the surname of the composer instance. In this example, Milton Babbitt and Clarence Barlow are instances of the composer class, with the attributes name and surname set to Milton and Babbitt for the first instance, and Clarence and Barlow for the second. In the Clarence package, we pass instances of the part class to the pros function for final compiling of the score. The most important argument for a part instance in Clarence is a set of key value pairs to specify notes, their onsets, and their durations. For this, we use a dictionary, which in Python is an association of keys to values. A dictionary is written using curly braces and has the following form. As you can see, the associations can happen from keys. Here I have used strings only, to any type of values. In this example, the first two values are strings, and the third value is the integer 100. We can retrieve values from Python dictionaries using their keys. This is done in the following form. If the key exists in the dictionary, the result of this query will be the value associated with the key. In this case, we would receive the string value 1 and the integer 100. The dictionary argument for a part instance in Clarence requires at least two mandatory keys, note and onset. These are essentially the same as in Milton, with note representing a list of MIDI key numbers or note names, and onset representing the incrementing time slots where each note should occur. To see this in action, let us recreate the simple sequence of notes we wrote earlier in LilyPond using Clarence, after having imported the Clarence package. The above code generates a sequence of notes based on the MIDI key numbers provided, with each note occurring a 1/4 note after the other, as specified by the unset values. For a part instance, passing a list of two or more lists of notes and unsets instead of a single list will again result in a polyphony within the same part instance. Here is an example. In this example, each sublist in the note and unset lists represents a different voice or layer, allowing multiple voices to be printed simultaneously within a single part instance. Of course, we can also have any number of part instances, each representing a different instrument or voice in the score. For example, we can create two part instances and then pass them to the pros function. This allows us to build more complex polyphonic textures by combining multiple multi-voice part instances. This was a short introduction to the basics of the two packages Milton and Clarence, to hopefully give you a very rough idea of what these packages are capable of. The functionalities of these packages far exceed the brief examples I have shown here, but I hope this introduction provides a glimpse into the flexibility they offer. I'll include links to their pages, which should be consulted for further learning. I will now move on to the final part of my lecture. In this section, I will be using Milton and Clarence to simulate one of my favorite pieces of music, the Mode de valeurs et d'intensité by Olivier Messiaen. While I will still comment on some programming aspects, as I will be using new features of these packages and the Python language, my focus will remain on the music. I should also mention that I won't be providing an in-depth analysis of the composition itself, as there are already plenty of scholarly writings on this historically significant work. Instead, I will focus on explaining the overall structure of the music, which will be necessary for generating it in Python. I have chosen this piece because of its importance in music history, as it marks the beginning of the integral serialist movement in the 50s, and because it offers a suitable playground for demonstrating an algorithmic approach to music composition due to its more or less rigid and structured development. The composition lasts around 4 minutes, so I would suggest we listen to it first, here in a performance by Yuji Takahashi. The overall structure of the composition is as follows. The piece is composed out of three so-called modes. Each mode is characterized by specific pitches, durations, articulations or attacks, and dynamics. Overall, the three modes encompass 36 pitches which are distributed across the three modes, with each mode containing a unique set of 12 chromatic pitches. 24 durations which constitute the rhythmic material of the composition, with each mode featuring its own rhythmic structure. 12 attacks define how the notes are articulated or played throughout the piece, and 7 dynamic marks which specify the loudness levels for each note, ranging from very soft or pianissimo to very loud fortissimo. Messiaen's approach is systematic. From the above-mentioned set of parameters, he creates the three modes, which ultimately are utilized to form the final score. Each of the three modes is composed of a descending set of pitches that collectively encompass the 12 chromatic notes spread across a specific range of the piano. Each pitch in these modes is associated with a specific duration and intensity and its own articulation. This results in a total of 36 unique sounds, each comprising a distinct pitch, duration, intensity, and articulation. These notes remain consistent in terms of their properties throughout the entire composition. Up to this point, everything seems to be rigidly structured, but Messiaen's approach in placing each sound doesn't adhere to a strict serialistic mindset. Instead, his choices are guided by more practical and pianistic considerations, such as whether hand crossings and large jumps are feasible, and most importantly, by his sound imagination. To create our simulation of this piece, I create a Python file by creating a text file, giving it a name, and ending the name with .py. The first step is, after of course having imported the necessary packages and initialized real-time MIDI, to build the three modes. To do this, I would first represent the pitches of each mode as a list of MIDI key numbers. Next, looking at the durations in each mode, they are arithmetic progressions starting with a 30-second note for mode 1, a 16th note for mode 2, and an 8th note for mode 3. We could write these progressions by hand, but I prefer to use a list comprehension for a cleaner code. Dynamics range from very soft pianissimo to very loud fortissimo. Out of the 128 possible velocity values for the intensity of a sound, I choose velocity 37 for pianissimo and velocity 127 for fortissimo. 37 is soft but still loud enough to be heard among louder velocity values. The intermediate dynamic levels are spaced equidistantly between these two extremes, resulting again in an arithmetic progression for the intensity of the sounds. To specify the articulation order for each mode, I use the following pattern. The string closing parenthesis indicates a legato from one note to its neighbor. Exclamation mark denotes a staccatissimo. Dot stands for a staccato. Dash represents tenuto, and the bigger than sign signifies an accent. For notes that require multiple articulations, I use a list of such strings instead of a single string. For example, this would place both a tenuto mark and an accent mark on the same note. Here, the attack form number 8. Notes that don't have any specific articulations will simply receive an empty string. Having defined the parameter sequences as they appear in each mode, to obtain the final modes, I only need to zip the corresponding items from the parameter lists together. To generate the final composition, I need to determine the specific order of the notes for each voice as Messiaen used from each mode. Since this order does not follow any regular pattern and is freely chosen by the composer, I need to manually specify the index numbers of the notes from each mode as they appear in the piece. For example, the beginning 4 notes of the upper staff are derived from the first 4 notes in mode 1. Since in programming it is common to start counting indices from 0, I enter the index number 0 for the first note. The next note in the upper voice is the second note in mode 1, which corresponds to index number 1. The subsequent notes for the rest of the first line follow the indices 2, 3, 5, 4, 6, 9, and 10. To save time, I have already prepared the complete indices of notes from each mode used by Messiaen to form the 3 voices of the piece. We have now already created the 3 modes, which contain the parameter collections as we have specified. There is one other important parameter we need for use in Milton and Clarence, the onsets of each note. To compute them for each voice, based on the list of note indices from a particular mode, I use an accumulation of the durations. For example, to obtain the onsets for mode 1 with indices 0, 1, 2, 3, 5, I can retrieve the second element from our mode data for each note. Remember, we passed the mode durations as the second input to the zip function. Retrieving the second element from the mode data can be done with an iteration through the nodes and extracting the duration items. Using a list comprehension, this can be done very easily. The result can then be passed to the accumulate function to obtain the actual onsets. In terms of durations in the final composition, although most notes use the durations we have already generated using our code, Messiaen introduces some deviations for certain notes, most of which occur in the upper voice. This is likely also due to the lack of control over durations in the highest register of the piano caused by the absence of dampers. Because of this lack of sustain in the upper notes, there is practically no benefits in holding the finger down for longer durations, as the result is almost the same as simply striking the key shortly. These deviations in some durations are likely due to pianistic considerations. For instance, when the same hand has to switch between different registers or voices, durations are shortened to make such passages playable. These adjustments to the computed durations must be introduced into the code manually. Since there are no deviations in the duration in the middle voice, here I have used 2 loops to iterate over all onsets of the upper and lower voices, correcting the durations wherever necessary. Having written these steps, I can now use Milton's note function for generating MIDI note data by iterating over the parameter lists we have created in the code. And so at the end, by having created the data for the 3 voices, we can now pass these data to Milton and Clarence to generate the real-time MIDI and the score at the same time. Using Milton, we not only can now listen to the music in real time as we have done so far, But we can also write an output MIDI file by passing a string argument as the file path to Milton's pros function. Before we listen to our complete simulated Messiaen piece, let's also take a look at the LilyPond file that Clarence has automatically generated for us. Although many more settings can be adjusted within Clarence, which I intentionally did not mention to keep my talk concise, we also always have the flexibility to make further fine-tunings directly in the generated LilyPond file. For example, if we want to use a bass clef for the first two notes of the lower staff, as is done also in the original published score, we can easily do this in LilyPond. Similarly, to stay true to the original score, we can rename the first note of the upper staff enharmonically to E flat instead of D sharp. And mark the first 6 notes of the upper staff with an octave indication. Here at the top, we have the MIDI file, which have been generated for us by the Milton package. And at the bottom, we have the final score, which have been generated by the Clarence package. Let's now listen to the final composition. In conclusion, reflecting on our process for creating this composition simulation, we started with the broad elements constructing the basic framework of the piece. Subsequently, we manually adjusted the finer details which could not be automated due to aesthetic, practical, or other musical considerations. Our approach was bottom-up. We first established the overall structure and then refined the details as needed. This bottom-up methodology guided us throughout the coding of Messiaen's piece.